The heart and major blood vessels get all the attention, but physically, they're just the plumbing. The actual life-sustaining work of the cardiovascular system, the delivery of nutrients and the removal of waste, happens entirely on a microscopic scale. Let's map out exactly how blood moves through this network. Blood flows from the highly muscular arterioles into the metarterioles, past these small gatekeepers called precapillary sphincters, and finally into the true capillaries before draining out through the venules. Blood doesn't flow through these beds in a continuous, even stream. As we see here in the text, it flows intermittently, turning on and off every few seconds or minutes. This is called vasomotion. The precapillary sphincters open and close based on local tissue conditions, primarily the concentration of oxygen and local metabolites. So the microcirculation is a highly regulated dynamic network. But once those precapillary sphincters open and blood enters the actual capillaries, we have to look at the physical forces that control how fluids and gases cross the vessel walls. First, we need to separate the three distinct mechanisms of exchange. The text outlines that gases move via simple diffusion, and large lipid-insoluble molecules get packaged into vesicles through transcytosis. But the massive, efficient movement of fluids requires bulk flow, and bulk flow is driven entirely by pressure. To understand bulk flow, look at this cross-section of a single capillary. 4 specific pressures are at play here, collectively known as the Starling Forces. Pushing outward, we have Capillary Hydrostatic Pressure, or CHP, and Interstitial Oncotic Pressure. Pushing inward, we have Blood Colloid Osmotic Pressure, or BCOP, and Interstitial Hydrostatic Pressure. We determine the net filtration pressure, or NFP, by plugging these forces into the Starling equation shown here. Because the interstitial pressures are usually negligible, the math really comes down to a battle between 2 dominant variables: capillary hydrostatic pressure and blood colloid osmotic pressure. Hydrostatic pressure is the physical force of the fluid actively pushing outward against the vessel wall. Osmotic pressure, generated by large plasma proteins trapped inside the blood, pulls water back in. They create a continuous microscopic tug-of-war. Let's walk through this microscopic tug-of-war from start to finish. This diagram tracks the changing pressures as blood travels. At the arterial end, blood just arrived from the heart, so the hydrostatic push is strong, around 35 millimeters of mercury. Subtract our steady osmotic pole of 25, and we get a positive net filtration pressure of 10. The result is filtration. Fluid is forced out into the tissues. Now, stop precisely in the middle of the capillary. Because water just left the vessel, hydrostatic pressure has dropped to 25. The osmotic pole remains steady at 25. 25 minus 25 is 0. Here, there is no net movement of fluid. Finally, we reach the venous end. The large plasma proteins haven't gone anywhere, so our osmotic pole is still rock steady at 25, but our hydrostatic push has dwindled to just 18. This gives us a negative net filtration pressure of -7, meaning fluid is actively pulled back into the capillary. But the math doesn't perfectly balance out. As we see in the text, across your entire body over a 24-hour period, about 24 liters of fluid are filtered out, but only 20.4 liters are reabsorbed. The lymphatic system steps in as the essential physiological safety net, picking up that 3.6-liter deficit to prevent your tissues from constantly swelling with edema. Once blood exits the capillaries, it gathers in the venous system. Veins are highly distensible, low-resistance vessels that store roughly 60 to 70. To push this blood back to heart, the body relies on physical forces detailed here, like muscle contractions, changes in intrathoracic pressure during breathing, and the gravitational pressure of your posture. To map how the heart handles this returning blood, we use a cardiac function curve. This graph plots right atrial pressure on the x-axis against cardiac output on the y-axis. According to the Frank-Starling mechanism, as venous return increases, atrial pressure stretches the heart muscle, and cardiac output rises linearly until it hits a physical plateau. Now let's overlay the vascular function curve onto this same graph. This line illustrates an inverse relationship. As right atrial pressure drops, venous return naturally increases. But look at this flat portion on the left side, called the knee. When atrial pressure drops into negative values, the thin-walled veins collapse, cutting off any further increase in flow. The exact intersection of these two curves is your body's steady state. It represents the precise physiological balance where the volume of blood the veins deliver matches the exact volume the left ventricle ejects. Let's lock this down. The entire microcirculation system can be organized into 4 core nodes: the anatomical pathway, the mechanisms of transcapillary exchange, the hydrostatic and osmotic Starling forces, and the physical dynamics of venous return. For calculation problems, rely on this visual framework. Blood colloid osmotic pressure remains constant throughout the capillary bed, while capillary hydrostatic pressure gradually falls from start to finish. Keep these high-yield facts ready for quick recall. Pre-capillary sphincters dictate flow based heavily on oxygen demand. Remember, simple diffusion is strictly for gases, and hydrostatic pressure is always your outward push. If you have a subjective exam, practice structuring long-form answers for these specific prompts. Be ready to detail the daily lymphatic deficit and to explain exactly how respiration alters central venous pressure. Let's run a quick test. Which structure regulates intermittent capillary flow? The precapillary sphincters. What is the primary mechanism for oxygen exchange? Simple diffusion. And which Starling force acts as the main inward pull? Blood colloid osmotic pressure. Internalizing these pressure gradients and mathematical balances provides a mechanical framework for how the cardiovascular system sustains life, and a diagnostic lens for when those physical forces fail.